to call this lesson AP Calculus 6-8 Part 4. This is integration of natural log functions. In order to understand how natural log integration works, we have to first recall what we did when we took the derivatives of natural logs. Remember, when we took the derivative of a natural log of x, we took the derivative of the x part and put it over the original x part. So the derivative of natural log of x would be the derivative of x, or 1, over the original x, 1 over x. Then we graduated kind of into natural log of a function here, and we said that the derivative of that natural log of u would be the derivative of the u part on top over the original u part on bottom. So essentially what we're looking for here when we're trying to integrate natural log functions or functions, now the functions that you're looking at are not going to have natural logs in them, so there's not going to be any indication that it will be a natural log function, but what you need to look for if it is a natural log function is the derivative of the bottom on top. So the derivative will be on the top and the original will be on the bottom. So if I have this, the integral of dx over x, well, the derivative of x is dx. So we've got the derivative over the original, which would be a natural log situation. So the answer to this would be the natural log of the absolute value of what's on the bottom plus c. Here, the derivative of u is du, so I've got the derivative over the original. Whenever I have the derivative over the original, it's very likely to be a natural log situation. So here, since this is the derivative of u, then the answer to this would be natural log of the absolute value of u plus c. Now, eventually with what we're doing with the geometry and things, that absolute value is going to be dropped. For now though, put it in to make sure you're getting all the points that you need. Here we've got the integral of 2 over x dx. Now if I think about that one, we learned in our properties that we can take any constants out of the integration. So I'm going to take that 2 out to the outside, and then I'll have a 1 over x dx. Well, if you think about that, that dx could be on top. That's the same thing as dx over x. So it's the derivative over the original. So this is a natural log function. I've got a 2 times natural log of the absolute value of the bottom plus c. And it's that simple. If you have the derivative on top over the original, then it's going to be a natural log situation. And some of these are easier than others. Sometimes you will have to put in a little extra something, like you might be missing a 4 and you have to put a 4 on the inside and a 1/4 on the outside to offset it. That kind of stuff still happens. But you should have a derivative over an original to have a natural log integration situation. Here, if I take the derivative of the bottom, I would have a 4 dx. So I'm missing the 4 on the top to have a derivative over an original. Now understand, this is the same thing as 1 over 4x minus 1 dx. I could start that problem off either way. So if it's easier for you to understand that the dx is to the side, that's fine. It doesn't have to be put on top. It can be put to the side, and then you could do the math. But if I want this to be the derivative of the bottom, if you think about what the derivative of the bottom is, that would be a 4. So the top needs a 4. If I multiply 1 by 4, I get 4. And if I've multiplied by 4, then on the outside, I still have to offset that with a 1/4, so that I've really only multiplied by 1. So now I have the derivative over the original. That is a natural log situation. So I've got 1/4 natural log of the absolute value of 4x minus 1 plus c. And that's my final answer. Keep in mind, we could still have definite integrals with these where we have to plug the values in. For this one, the bottom is x squared plus 1. The derivative of x squared plus 1 is 2x. Well, I have the x. I'm missing the 2. I need a 2 on the top. When I put the 2 on top, I offset that on the outside with a 1/2. Now I have the derivative over the original, so I keep my 1/2. That is a natural log of the absolute value of x squared plus 1 plus c. So very simple. You need to train your brain to look for derivative over the original. This shows up quite often. So this is one of those things that you're going to see it quite a bit. So you need to really focus on what you're looking for with these different types of integration problems. For this one, the integral of the bottom is 3x squared plus 1. That's exactly what we have on top. So it's a natural log situation. I don't have to put anything in front because I have everything there that I need. So this is just the natural log of the absolute value of the bottom, x cubed plus x plus c. And we're done. So you're looking for derivative over original for these problems. For this one, it looks more complicated because we've got some trig functions in there, but if you think about what you're looking at here, what is the derivative of tangent? Well, the derivative of tangent is secant squared. So we have the derivative over the original. So that one doesn't need anything tagged in front. It's already a natural log situation. That is the natural log of the absolute value of the bottom plus c. No work there at all, just recognizing that you've got derivative over original. Here, the derivative of the bottom is 2x plus 2. Notice up here we have x plus 1. What do I need to multiply the top by to make it a 2x plus 2? Hopefully you're saying we need to multiply the top by 2, and it will be a 2x plus 2. I'm going to offset that on the outside with 1/2, and then I'm going to go from there. So I'm going to keep the 1/2. I have the derivative over the original, so I've got a natural log of the absolute value of x squared plus 2x plus c. For the next one, the derivative of 3x plus 2 is 3. So I need a 3 on the top. Right now it's a 1, so I'm going to multiply the top by 3, which means I'll offset it on the outside by 1/3. And that is a natural log situation, so I've got 1/3, the natural log of the absolute value of 3x plus 2 plus c. Sometimes we're going to have to use u-substitution with natural log integration. And if you look at this, if you think about the derivative of the bottom, that would be 2 times x plus 1 times 1. Well, we can't get this to equal that without u-substitution. In other words, we have the 2x that we need, but it would need a plus 1 in order to be able to do this and have a true derivative over the original. So we don't have that here. So we're going to have to figure out what to do to make this one a natural log situation. And if you think about u-substitution, this isn't as bad as it looks. What I'm going to do is I'm going to let u equal this x plus 1 part. Remember when we did u-substitution originally and we had something like this, the integral of something like this, we let the u be the inside part. So that's what we're doing here. We're letting u equal x plus 1. And so then du is just dx. Okay, so now let's look at what we get when we substitute this. We have the integral of 2x over u squared times du. Well, we have that extra x part here, so let's replace it with what x equals. Well, if we move that 1 over, isn't u minus 1 equal to x? So I'm going to put that on top. That's 2 times u minus 1 over u squared du. And then with this one, if I distribute, I've got 2u minus 2 over u squared du. Now, this one looks tough. It is not the derivative over the original, right? But if we think about the derivative of u squared, wouldn't that be 2u? So we sort of have the derivative here, but it looks a little bit different than what we need it to be. So if I think about what a fraction like this means, couldn't I separate that out and make it 2u over u squared minus 2 over u squared? And so if I try to integrate these two pieces separately, now I really should put the du here and here because they both have a du there. If I try to integrate this, well, isn't 2u the derivative of u squared? So wouldn't that, and I'm going to move it up here, wouldn't that be the natural log of the absolute value of u squared? Minus, now if I'm trying to integrate this, isn't that the same thing as 2 times the integral of u to the negative 2 du? And so if we're thinking about trying to integrate that, we're going to use our old method. That's not a u-substitution. That's just a simple integration. We're going to have the 2. This is going to be u to the -1 over -1. We have the plus c. So here's the natural log part, or natural log of the absolute value of u squared minus, now I can put that u to the -1 on the bottom, and that's going to be a minus a negative, so that'll be a plus 2 over u plus c. And that would be almost my final answer. I just have to resubstitute the u's next. So that would be the natural log of the absolute value of x plus 1 squared plus 2 over x plus 1 plus c. And then thinking about your properties for the logs, this 2 could be brought out to the front. So that's the same thing as 2 natural log of the absolute value of x plus 1 plus 2 over x plus 1 plus c. This one looks very different, but it's really not too bad if you think about what you've got here. Normally when we have an integration and it involves an answer with a natural log in it, there were no natural logs in the original problem, okay? And so that presents something that looks a little bit different to us. But if we just think about what we've got here, it's not as difficult as it seems. Here we could let u be that natural log of x, because otherwise we don't know what to do with it. There's no rules for taking the integral of a natural log. So if you have a natural log shoved in here, then that's going to have to be part of our u in order to be able to do it. So we're going to let u equal natural log of x. And if you think about what du would be, well, isn't the derivative of natural log just 1 over the original times dx? So if you look at what we've got here, if we substitute, we have that u on the bottom, and then isn't 1 over x dx our du? So that's just du over u. Well, how do we integrate the derivative over the original? It's a natural log. So the answer there would be the natural log of the absolute value of u plus c, and then we resubstitute our u. So natural log of the absolute value of natural log x plus c. That's very strange looking, but there's nothing that says we can't do that. So this takes us to the antiderivative or integration of tangent x dx. This is a very important concept to understand when we're dealing with natural log functions. Because if you think about what we know about integration of trig functions, we could only integrate the trig functions based on what their derivatives had been. And so if we think about that, the antiderivative of sine x dx, well, that was negative cosine x. The antiderivative of cosine x dx was sine x. And then we did not have an integration for tangent. There was no way we could do tangent because the antiderivative of secant squared x dx is tangent. There was no derivative of a trig function that gave you tangent as the answer. So we're limited right now to our trig functions being, or the integration of trig functions being what we started with, like the opposite of our derivatives. Well, knowing how to do natural logs changes that for the tangent function and for the cotangent function. If you think about what tangent means, and if I ask you to integrate tangent, well, there is no rule for the integration of tangent yet. So the only way we could even try to integrate this is to substitute it for something that it equals. And if you think about your trig identities, isn't tangent the same thing as sine x over cosine x? And if you think about what this is, isn't the derivative of cosine negative sine? So we almost have that derivative here. We need a negative. So if I put a negative in the front there on top, I need a negative in the front on the outside to offset that, so I haven't changed the value of the problem. Now, if you think about it, the derivative of cosine is negative sine. We have the derivative over the original. Whenever we have a derivative over the original, that's a natural log situation. So I keep the negative, That is natural log of the absolute value of cosine x plus c. That is the integral of tangent. So now we have a rule for tangent. If you don't want to memorize this, that's fine. You can do this every single time. So now that we have a rule for the antiderivative of tangent, I want you to see if you can use the same thinking and figure out what the antiderivative of cotangent is. Go ahead and pause the video and see if you can get that, and then I'll show you how to do that in just a few minutes. So hopefully you remember that cotangent x is cosine x over sine x, and the derivative of sine is cosine. So if the derivative of sine is cosine, we have a natural log situation here. That is the natural log of the absolute value of sine x plus c. So the antiderivative of cotangent x is the natural log of the absolute value of sine x plus c. So now that we know how to integrate dealing with natural logs, we can find or have all of the trig functions antiderivatives. So sine and cosine we already knew. Tangent we just derived. Cotangent we just derived. So the other two are secant and cosecant. The antiderivative of cosecant, and you'll just need to memorize this, is the natural log of the absolute value of secant x plus tangent x plus c. Now recall when we did the derivative of secant, wasn't it secant tangent? So here it's very similar. You've just got a plus in front with the absolute value and a natural log. So it's very easy to memorize these. The antiderivative of cosecant x dx is the negative natural log of the absolute value of cosecant x plus cotangent x plus c. So not too bad to learn those. You could look online and see how those are derived if you're interested in that. It is a pretty long, involved process. It's not that difficult. The amount of time it takes doesn't justify showing you that in video form. So just memorize it and understand how to find the antiderivative of secant and cosecant. So now I'm going to do a definite integral involving a trig function. With this, you need to understand that if we're trying to find the antiderivative from 0 to pi over 4 of the square root of 1 plus tangent squared x dx, you need to recall that this is one of your trig identities. Remember, 1 plus tangent squared x is secant squared x. So I can replace what's underneath the radical sign there with secant squared x. And then the square root of secant squared x is just secant x. And then we know the antiderivative of secant x is the natural log of the absolute value of secant x plus tangent x. And we're going from 0 to pi over 4. So I'm going to plug in pi over 4 first, and then I'll plug in 0 second. So this will be the natural log of the absolute value of secant pi over 4 plus tangent pi over 4 minus the natural log of secant 0 plus tangent 0. If I use a unit circle and I think about pi over 4, that's at 45 degrees. The two coordinates of the ordered pair, square root of 2 over 2 and square root of 2 over 2. So secant at pi over 4 is the inverse of the cosine. Cosine is square root of 2 over 2. So secant is going to be 2 over square root of 2 at pi over 4. Tangent at pi over 4 is square root of 2 over 2 over square root of 2 over 2, which is 1. And then we have the natural log. Secant at 0, here is 0, that is 1, 0. The inverse of cosine is secant, so that will be 1. So secant 0 is 1, plus tangent at 0 is 0 over 1, which is 0. So we have the natural log of the absolute value of 2 over square root of 2 plus 1 minus the natural log of 1 for our final answer. And sometimes in AP Calculus, depending on what you're asked to do, they'll want this as a decimal to 3 decimal places. Sometimes they'll want you to leave it like this. Certainly if it was a non-calculator based, I would leave it like this. If it was not, I would consider making it the decimal 0.881. And if you put that in your calculator, you can see that that's what that is.